A'udhu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. In today's lecture, we will talk about semiconductor nanowires. This topic has been taken from the course outline of nanophysics and technology, having the course code of PHY445. In today's lecture is basically divided into several parts. Initially, in the first part, we will discuss the introduction about nanowires, and then the synthesis technique to prepare the nanowires. Some of the different nanowires, including pseudowires or freestanding wires, that is the types of nanowires. At the end, we will discuss the properties, special properties of nanowire, and finally we will go through the application where we can utilize these nanowires in advanced technology. First, we need to know pseudowires. What is that and why we use it? It is actually the wires which are enclosed in other materials, and there are several techniques to prepare such nanowires. There is some very interesting morphology. Some of the techniques are the lithography and etching, and electrostatically induced wires are produced in it, and some of it are the strain induced wire with the, and some of the growth or pattern on the surfaces, and that which nanowire morphology is produced. The pseudowires are basically prepared by the lithography and etching technique, and this is very special technique for the formation of the wires morphology. For this purpose, initially we need to prepare the 2D quantum wells, and that is coated with some resistive materials, and then the pattern is created within it, and finally the other material is etched to prepare the nanowires. In some cases it is overgrown again to shield the wire, and the disadvantage of such wires is that it has optical and electrical dead layer because of defect due to etching. The electrostatically induced nanowires are created. We have example of GAAS and AlGAAS as well, in which aluminum is doped, and in these wires there is a creation of Schottky contact, which is actually the metal semiconductor contact, and a voltage is applied on it, and as a result of this application of voltage, rises or lowers the band. The band gap is changed. So as a result of that, the creation of nanowire for hole and electron at certain voltages. So there are split gauges to slightly separated metal strips, and in which potential minimum creates of wires of variable width. The disadvantage of this particular nanowire is that the potential minima is not very deep, is only used for low temperatures. We have some strain induced nanowire that was initially discussed, in which strain is used to create the nanowires. Again, initially in this process the 2D quantum wires is used, and carbon is used for the strain creator, or maybe a stress is applied on it which creates the strain through it, and as a result of this stress, wires through this strains are produced. So the nanowires created in this process has some disadvantages, and some are mentioned here, that it has very small potential, is only for low temperatures. Some particular and very interesting shaped nanowires are V-grow nanowires, and for that purpose we need to prepare the substrate and V-shape due to different etching directions, and this is grown it's grown on a barrier material, and the growth of barrier material is made, and then finally the growth of second barrier material to sharpen the grow again. So this is some image of the V-grow nanowires, in which stepwise the nanowires are created, and the nanowires are given the shape of V. Therefore, that is why it's called as V-grow nanowires. cleavage edge growth as well, in which there is a growth of quantum well, and rotations occur. The same sample is rotated through it, and as a result of this, there is a growth of second quantum well, and the wires are created. But for this process, the low temperature is required. There are different techniques to prepare the nanowires or prepare the nanowire morphology. So it depends upon the nature of material and the method followed. So the general method what are used to create the nanowires are the VLS. That is, some of the methods are discussed here. One is the vapor liquid solid method, and some of the modification of VLS methods are the chemical vapor deposition method, and laser ablation catalytic growth method is also discussed. And at the end we have some low temperature VLS method. Further, we have some other technique in which include liquid, solid, fluid. So that is FLS, that is called as fluid liquid solid mechanism, and we have SLS, that is the solution liquid solid mechanism. And we have another method for the preparation of the nanowire, that is OAG, is called as oxide assisted growth. Here is the morphology of nanowires. We can see very clearly the nanowires are arranged in a very regular pattern, and this is image has been taken from the TM. We want to discuss some of the method to prepare the nanowires over here in this presentation. The first one is the vapor liquid solid method. This is basically the phase diagram to prepare such to follow the phase conversion in this method is given here. In this case, we have this have phase diagram, and we have liquid is and solid is line, from which liquid is converted into solid, and solid is converted into liquid. So we have three steps for it in which the nanowires are created. So we can follow this particular lever rule to go through this phase transition. So we can get information from the phase diagram, but keep in mind, again, it depends upon the nature of material. We can create the nanowires of different semiconductor material. This is a really very general phase diagram about vapor liquid solid method, but for special case, it varies. The liquid is and the solid is line vary from material to material, and even the the value of the transition from solid to liquid or from liquid to solids, that also varies. So for special case, when we consider special semiconductor material, we need to develop that particular phase diagram for that. This is something about the vapor liquid solid method. This is again a very general explanation of this method, or a very general phase diagram of this method. Again, if we want to specialize it for a particular semiconductor material, we need to there will be modification in this process. It depends upon the nature of that particular semiconductor material and its conversion from liquid to solid or solid to liquid, maybe particular phases. So there is a coexistence of three phases as well in this method, and the lowest temperature where system is still totally liquid, that is the eutectic, and there we have a minimum liquid is curve for this, and solid and solid plus liquid phase consist of only one material. So this is again a very general phase diagram for the vapor liquid solid method, where we can create such materials. We have vapor liquid solid method as well, that is finally used for different type of materials. Some of the examples are given, just like we have binary group 3 to group 5 material, in which gallium arsenide GAS, GAP, INAS and INP, that comes. We have ternary materials, ternary semiconductor material, that is composed of group 3, the combination of group 3 and group 5 elements. In that we have GAS /P or maybe INAS /P. So similarly we have some binary material that is composed semiconductor material that is composed of group 2 and group 6, in which we have ZNS, ZNSC, CDS and CDSE. So that is actually some of the example I did. So we have pseudo binary phase diagram for such type of materials, especially for the GIS semiconductor material. Here we have different phases for that is the combination of AU and AU is doped in GAS. So what happen, there will be on right side we have GAS in liquid form, and the combination of liquid and GAS, and on the right side we have AU. So they are combined and there is a particular point where it is mixed with each other, and that particular material is prepared, and we can get the morphology. We can get such morphology from such this particular process on this semiconductor material. We have another method, that is the vapor liquid solid method. That is the combination of vapor, liquid and solid. Again we need to have a phase diagram for that, in which there is a conversion between liquid to liquid to solid or liquid to vapor, and in which there is a transition of that particular phases. So we have a critical diameter for that, and it is also used for a particular sort of material and in this case the liquid catalyst clusters are stable in equilibrium. We have a particular equation for it that describes the value of D, and that is actually the different parameter used in this equation are the surface free energy, the gas constant temperature, and the concentration of semiconductor component in liquid alloy, and similarly CY is the equilibrium concentration. So we have some problem and with this method as well, that in fluid according to temperature the critical diameter is about D is equal to 0.2 millimeter achieved from this method. So this is some of the method which is also used for the creation of for the preparation of nanowires. We have chemical vapor deposition method that is widely used and is very famous. So especially we can prepare gallium nitride nanowires out of it, CVT from CVT reactors. In this case Ni catalyst and Si substrate is made with the 0.5 MNI and NO3 twice 6H2O. So in this case it is dried in O1. This is actually the synthesis process or the preparation process of this particular nanowires, and this is formation of Ni island on Si substrate. Further Ga and Jan powders are included in the inner reactor, and hydrogen in the outer tube to minimize side reaction until 700 degrees centigrade, and ammonia gas is present in the inner reactor. So what happened, there is a start of nanowire growth, and nitrogen gas is used during cooling phase. So this is also used for the preparation of nanowire morphology. Here we can see the nanowires that are randomly oriented, and these nanowires are prepared with the help of CVT or the chemical vapor deposition method. We have the summary of nanowires which are produced and the minimum diameter of these nanowires. So these are a single crystal nanowires which are synthesized by different technique, and the minimum diameter are D in nanometer. So we have material just like GAS its diameter is achieved to be 3 nanometer, and it has this structure of zinc blende structure. So we have the ratio of component as a 1.00 Similarly we have another semiconductor material that is compound semiconductor, that is GAP, and we can achieve the nanowires with the minimum diameter of about 3 to 5 nanometer. It has also zinc blende structure. So some other compound nanometer, that is GASP and INP, and similarly INS, that is also comes in the nanometer range, which have respectively the diameter of the nanowire, that is equal to 4 and 3 to 5 or 3 to 5 respectively. And again all these three material have zinc blende structure. So further we have very simple some nanowires that are made from Z and S and having the minimum diameter of 4 to 6 nanometer, having zinc blende structure. Similarly, Z and SE is achieved with the minimum wire diameter of 3 to 5 nanometer, and it also carries the zinc blende structure. For the case of CDS and CDSE, we can also get the Urzite structure with the minimum diameter of 3 to 5 nanometer for this particular nanowires. And finally, we have also some of the nanowire that are achieved in the material that is SiGe, in which the concentration of G is changed, and it has diamond structure with the particle size of 3 to 5 with the diameter size of 3 to 5 nanometer. So we have the zinc blende structure that is shown over here, and the Urzite structure as well. So this is some of the nanowires we have today. We have already sent this prepared, and that has the minimum diameter, which is showing that it are very interesting nanowire. So properties of the nanowires, why is it so important to us that we want to have such a interesting morphology, that is the nanowire. So it has optical property, it has various interesting property, including optical property, catalytic property, and some other property as well. So we have PL characterization of some property. There says PL depends on our direction, so we have perpendicular and parallel for it. So it has intensity uniform along wires. I mean, a particular wire is intensity uniform, and it depends upon the angle of that. Some of the other property that there is the size, the property of nanowires also depends upon the size of that particular nanowires, and the photoluminescence spectra depends upon the size of the nanowire. Just like in quantum dots, we say that the optical property or the color that depends upon the size of the nanocrystal or the nanoparticle. In this case, it depends upon the size of the nano, or in other words, we can say the diameter of nanowires. So here we can see that when we are changing the diameter of the nanowire, coming in this case in the forecast at room temperature is from 10 nanometer till 15 nanometer, the peak is shifted to a lower energy. Here we can see the peak is broad. As we come from 10 to 15 nanometer, it is shifted toward the lower energy, and further shifting is found in the case of 20 nanometer. We see that the peak is very clear and visible in case of 50 nanometer. At the right side, we have this calculation at 7K. So we have this variation in which the peak is not shifted from one place to another place, but its peak is become narrowed. When increasing the particle size or the diameter size of the nanowires, the peak become narrow, and we can see that the peak size from at 10 nanometer is very different from the peak size at 50 nanometer. So this clear change occurs due to this the change in diameter size. So we have some other property of the nanowire that are the polarized excitation and emission process, which is very interesting for the optical properties of the semiconductor material. So we have parallel polarization and perpendicular polarization for that, and that value has been given here. So we see that there is a broader change in the different curves in this two diagrams from each other. So this is one of the property of the nanowires as well. It has very interesting thermal conductivity or lower thermal conductivity we get from the nanowire morphology. The thermal conductivity is calculated using the equation that K is equal to 1 over 3 CVVL, where CV is the specific heat, V is the velocity of photon, and L is the mean free path. So the mean free path of photon in solid is in nanometer range. So what happens that the nanometer, nanowire morphology gives us interesting thermal conductivity that is often used for thermal insulation processes. So we have alteration of phone transport in nanowires has more boundary scattering that changes in phonon dispersion relation, and it also causes the quantization of photon transport, and the final outcome is that the thermal conductivity is reduced. So we have this thermal conductivity for different nanowires, and we see that there is drastic drop in the thermal conductivity at different diameter size nanowires. We see when we are coming from lower diameter size toward the higher diameter size of this particular nanowires, then thermal conductivity is increased. But definitely for the thermal insulation we need material that have lower thermal conductivity. So here we can see that a material that is that is nanowires with its wire diameter of 22 nanometer that carry very low thermal conductivity in the range of 25 to 350 K, where the same material when its particle size or diameter size for the nanowires is increased to 115 nanometer. So there is a drastic change in the drastic increase in the thermal conductivity. Here we can also see how the thermal conductivity is changed with the changing the particle or diameter size of that. So doping is also possible. The dope material is also possible to have nanowire morphology, as we saw in this last table. Some of the materials are doped here, just like especially in this case and in this case and in this case. So we can also get nanowire morphology from such material, and in that case we can see here that doping also cause we can get the nanowire morphology from that, and we can use it in various applications. So these nanowires are used in has very interesting application. It is especially used in nanowires heterostructures, where we have axial heterostructures, just like in case of GAP and GAS heterojunction. It is also used in radial heterostructures, and it has application in superlattices as well. Further applications are of nanowires comes in the in optical property, in nanophotonics, where nano LEDs are made, that is from the combination of NP type nanowires and cross nanowire device, light crossing from point to power bus. We have nanoprobes as well, and that is used in atomic force microscopy, and such nanowires are also used for high temperature application and high current superconductor lasers and nano field effect transistor. So these are some of application of nanowires. So this is something about the understanding of nanowires, its properties, and say synthesis preparation technique of such interesting morphology, and finally the application of this material. Thank you very much for now for the today lecture.